Today, we want to look at definite integrals. We've been looking at definite integrals all week, but today we're actually going to use the notation of definite integral that we haven't been using before. The big idea is that we're trying to calculate the area under a curve and above an interval on the x-axis. And we're going to start with y as a function of x. So the area under the graph of a function and above an interval on the x-axis. What we're trying to do is use area is equal to length times width, but my length is not only changing, it's changing continuously. That's when we're going to have to switch to the definite integral. I want to do area is equal to length times width, but my length is continuously variable. I want to say area is length times width but if the width is the length of the interval from A to B, is the width of the interval from A to B, and the length is given by the height of the function, the length is changing continuously. It's not just staying constant at 5 for a little while and then jumping up to 7 and being constant at 7 for the rest of the time. It's changing continuously. And so that's when we have to switch from multiplication to integration. We have to use a definite integral because our function is changing continuously. The question came up is, when can we use this definite integral business? It's more than just area. The definite integral is just taking a y coordinate and multiplying it by some change in x coordinates. So the units of the definite integral are just going to be the units of y times the units of x. So in the case of area, area is equal to length times width. If the length units are meters and the width units are also meters, then our definite integral units will be area in square meters. If our function f of x, or the y, is measuring a rate in feet per second, and x represents time in seconds, then the units of the definite integral will be feet per second times seconds. The seconds cancel out, and the units of definite integral are feet. So the definite integral will be measuring some distance, because distance is equal to rate times time. If our the y equals f of x is measuring the density in kilograms per cubic meter, and x is measuring meters in cubic meters, the cubic meters cancel out, and the units of the definite integral are in kilograms. Here, mass is equal to density times volume. So we'll use this definite integral anytime we want to do multiplication, but where one of the factors is continuously variable. We use integration to do multiplication where one of the factors is variable. Integration is multiplication in which one of the factors is variable. Integration is for multiplication in which one of the factors is variable, specifically continuously variable. Otherwise, we could just do a bunch of rectangles, which is how we're going to think about this anyway. Any questions? Remember that our strategy For calculating the area when the length is continuously variable is to make rectangles. We flatten out the function, and then we can use multiplication so that we could just do length times width. So our strategy is to assume that the function is constant. We start by making rectangles. This means assuming that the function is constant for some small change in x on subintervals of AB. So our strategy is to first make rectangles. Once f is constant on subintervals of delta x of AB, now we get to use multiplication. So we evaluate f at some point xi in each subinterval to get the height, or to get a length. And so our area is going to be f at xi times delta x. Then we just add up all the areas of these rectangles. So our total area we add up all the rectangles. So each rectangle is an f at xi, that's our length, times a width, which is some small piece of the interval, delta x, and we just add up these areas. Here we are using n rectangles because I have it f at x1, f at x2, f at x3, all the way up to f at xn for the n rectangles. So this is our sigma notation to say add up the areas of the rectangles. And then since this is calculus, we use an infinite number of rectangles. Since more rectangles means a better approximation, use an infinite number of rectangles. So what we want is n to go to infinity and delta x to approach 0. We can't let delta x equal 0, otherwise, approaches 0. Can't let delta x equal 0, otherwise our areas are just going to be all 0. But the calculus step is to use an infinite number of rectangles. So in calculus, we can't plug in infinity, so we just take the limit as n goes to infinity. And this is an expression that is called a Riemann sum. This is the strategy that we've been developing this week. I want area to be length times width, but that only works if length is going to be constant. If the length is going to be variable, then our strategy is to drop down to the previous problem by assuming that the function, the length is constant for some small change in each subinterval, and then recognize that multiplication is just repeated addition. So we just add up the areas of all those rectangles. And then since this is calculus, we let the number of rectangles go to infinity. That is, we use an infinite number of infinitely thin rectangles. And so that's where the limit shows up. Because this is what calculus is really all about. The study of infinity. Trying to understand how infinity works. What needs to happen is that we need to go from using a finite number of rectangles, where n is finite. We need to understand what happens when we go from this discrete counting of rectangles to the continuous infinite number of rectangles. And so that's where the definite integral shows up. So we start with this Riemann sum. Which is the limit as n goes to infinity of the sum as I goes from 1 to n of length given by the function times width, which is some small but finite delta x, small delta x. The cool part is that when we go from this discrete sum, when we drop in this limit as n goes to infinity, we get the definite integral. And we still have the f at xi times delta x. But the f at xi, the discrete f at xi, becomes the continuous f of x. The delta x becomes the infinitely thin width. We say dx. And the limit as n goes to infinity of the sum as I goes from 1 to n just becomes the definite integral from a to b. So this is where the definite integral comes from. We need to understand how to compute a definite integral. reasonable question. I'm just doing f of x times dx, and I just traded some notation from a to b. So how does this help us? And so that brings us to our fundamental theorem of calculus. Let's let f of x be continuous on the closed interval from a to b. So we need to have a continuous function on a closed interval so that we can calculate the area under the curve and above the interval. The fundamental theorem of calculus says that the definite integral from a to b of f of x dx is capital F at b minus capital F at a, where capital F is an antiderivative of f. That is, capital F prime of x is equal to little f of x. Math is case sensitive, so if you're the type of person that writes in all caps, you need to stop. It's one of the good things that's come out of the internet. Typing in all caps means you're shouting, so now writing in all caps means you're shouting when you're writing. So don't shout when you're writing. Math is case sensitive. If you happen to be an architect, then I can let it slide for now, but only if you're an architect, because I think they have to write in all caps. I don't know why they shout. I think it's because they're at construction sites a lot, and so they end up having to shout at each other. That's my assessment of the situation. And if you think that I'm kidding about math being case sensitive, note that the function e to the x is a lowercase e, and if you start writing e to the x all the time, I tell you to stop once, and if you continue to write capital E to the x, I just start taking off points. I'm like, well, I don't know what this capital E is. When I ask you about the function little e to the x and you write this function capital E to the x, you never define what it is. Don't be like, oh, talk about the function I talked about. Don't be all inventing new functions. That's Captain Kirk's innovative solution to that Starfleet problem. Which really just means Captain Kirk is a cheater. You know what I mean? It's because we're supposed to think that Captain Kirk is a good guy that we see that Captain Kirk cheating on this Starfleet exam as a good thing. It's like, ah, look, he bucks the system and thinks outside the box. Also, by doing so, he completely missed the point of the whole test. It just means he doesn't understand the test, which means I think he's unfit for command. And given the prime directive in Kirk's actions, I think I'm right. You know what I mean? I mean, recut Star Wars or Star Trek from, you can easily recut Star Trek and make the Federation seem like bad guys because of Kirk. That's all I'm saying. Anyway, what are we talking about? Ah, yes. The fundamental theorem of calculus gives us a way to calculate this definite integral. The thing that we need to do is find these antiderivatives of the function. So an antiderivative is just a function whose derivative is little f. So an example.
Professor Rich, I have a quick question, please.
Uh-huh.
On here, you said f is the antiderivative of function. And on the bottom is the same meaning as f prime of x equal big F of x. I mean, f of x. So it's the same meaning, isn't it?
Yes.
Oh,
I'm saying capital F is an antiderivative of little f. And that means capital F prime is equal to little f. The IE means that means that capital F prime is equal to little f.
okay. And then it said to be continuous on A and B then. So when we see that interval, basically it means the big F of B minus the big F of A. It's like in the final minus the initial.
That's how we calculate the definite integral using the fundamental theorem.
One more thing, could you please scroll up the Riemann Professor? Yes, right there. When I see the limit n approach to infinity, so that represents the y, correct? Am I right?
No.
No.
That represents the number of rectangles.
But it go to the y, like the range direction. Am I right?
No.
No.
N is just counting the number of rectangles.
Oh. And then you said change in x is the approach to 0.
Yes, because as the number of rectangles increase, the width of each rectangle has to get smaller.
Smaller. We try to get the smallest as we can, correct?
More than just as small as we can. We get that we look at what happens as the width of each rectangle goes to 0, because the number of rectangles goes to infinity.
Okay, thanks, Professor Litch. Thank you.
So, as an example, let's suppose that we want to find the definite integral from 0. Yeah, it's fine. From 0 to 4 of 3x dx. So we want the definite integral from 0 to 4 of 3x dx. So what we're looking for the function is just 3x. So I'll draw a picture of 3x. That's just going to be a line. And we want the area under the curve, y equals 3x, and above the interval from 0 to 4 on the x-axis. And now you can see why I picked a line, so that we can just find the area. We just want to find the area of this triangle. So now we can know what we're headed for. So 4 times 3 is 12. So the area is 1/2 the base times the height. So we know the answer is supposed to be 24. Let's make sure that this antiderivative business gives us the 24 that we're looking for. So our function is 3x. That's little f. So little f of x is 3x. And we're saying 3x is the derivative of some function. So 3x is the derivative capital F of x. So 3x is the derivative of, well, it must be something x squared, because the derivative of an x squared is an x. So it must be an x squared. And let's see, to take the derivative, I get 2 times x to the first, but I need to have it multiplied by 3. So I need to keep the 3 and get rid of the 2. So 2 times 3/2 is 3. And then 2 minus 1 is x to the first. So here is the 3x is the derivative of 3/2 x squared. That is, 3/2 x squared is an antiderivative of little f. Because if we take the derivative of 3/2 x squared, we get 3x. So what we want to do is evaluate the function 3/2 x squared from 0 at 4, and then 3/2 x squared at 0. The way we can write that is we could say, oops, we're going to take 3/2 x squared. And if you draw a vertical line at the end of a function that says evaluate the function, and then we can say from 0 to 4. So I'll have 3/2 times 4 squared minus 3/2 times 0 squared. So that's capital F at B minus capital F at A. 4 squared is 16. 3/2 of 16 is 24. As predicted, the definite integral, doing this antiderivative business from the fundamental theorem of calculus, gave us the area under 3x and above the interval from 0 to 4 on the x-axis. Any questions?
Yes, Professor Lutz, very quick question on the example interval 0 to 4. We have 3x dx equal 3 over 2x squared. Where is that dx? Is it gone? That dx?
The dx is part of, we could think of the dx as being part of the integration process. So I have the integral from a to b of f of x times dx is equal to capital F at b minus capital F at a.
So on the bottom, the big f of x, we have 3 over 2x squared. That's an antiderivative.
Yes.
Where is that? So the dx will be gone. Am I right?
It's part of the, just think of it as part of the process.
Okay. All right, thanks.
Right. So here's what I'm asking you to do. Find an antiderivative and just do capital F at b minus capital F at a. So the dx is not part of this calculation on the other side.
That's why we plugged in the 4 and the 0. Got it.
No, we plug in the 4 and the 0 just because we're just following this
Yes,
process.
got it. I see it. Thanks.
All right. So we have a new notation today, the definite integral from a to b of f of x dx. In general, you just might say the definite integral of f from a to b. And then the of x dx part will be understood. That's just going to be, the dx is kind of just there to be the infinitely small delta x. Think of it as the width. So we're doing length times width. And this is how we can do length times width when our length is changing continuously. And we're just plugging in all the values from a to b into the function times the dx. And then this is how we can calculate it.
Oh, I see it now. So basically, the dx is equal big F of b minus big F of a. I got it. Thanks, Professor Lee. See it.
All right, this is what we're going to work on. The thinking is find the area under the curve and above an interval. We also want to think what other situations it's useful to do length times width instead of length, and instead of width, we could have some other thing that we're measuring. We want to understand what the units are going to be in that area equals length times width calculation. And we want to learn how to use this fundamental theorem of calculus to calculate area equals length times width if the length is continuously variable over the width. And it seems to involve the inverse operation of the derivatives that we were learning about before. So, like everything in math class, we have to learn it forwards and backwards. We have to learn how to find the derivative of a function, and now we're going to have to learn how to find an antiderivative of a function. All right. That's certainly a lot to think about. So that's going to be it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.